changes that we see in solar dynamics. Solar dynamics is, the changes in solar dynamics is actually pretty easy to determine comparatively. What I mean by that is the signals are pretty large. And I showed this zonal flow diagram. You've seen a similar one from Jinwei at 0.98 solar radius. You have on the upper panel, you have MDI and HMI. The lower panel is gone. But one different thing about this figure is instead of plotting contours of magnetic fields, what we did is plot in the upper panel the foot points of active regions as they emerged. And the coincidence that we see between this equatorward moving prograde flow and the sunspot positions is actually remarkable. You get an even better correlation if you look at the gradient of the flows rather than the flows themselves. The point of showing this was to show that, yes, we can get these very easily in dynamics. 0.98 solar radii, trying to find differences in structure, though, is actually very, very difficult. We don't have the normal sets of high degree modes that would help there, because the F modes, which are so useful in dynamics, don't play much of a role in telling us what the structure is. So what we decided to do is look at the signature of the helium ionization zone, which is at 0.98 solar radius. Now, why did we look at helium ionization zone? If you have a change in temperature because of magnetic fields, it'll shift the ionization zone slightly, and that will cause a change in the frequencies. But the change in the frequencies is actually a subtle change, and what we call it as a glitch signature. So an acoustic glitch is any sudden change in structure that has a wavelength smaller than your modes. So in the sun and other sun-like stars, there are two such glitch regions. A true glitch is present at the base of the convection zone, and a slightly more extended one is the depression in the adiabatic indices because of ionization, particularly helium ionization. So what do glitch signatures look like? And this is what the graph here shows. Can you see my pointer?
Yes, we can.
Okay, thank you.
Yes.
So what I show here is the response of frequencies to a glitch very close to the surface. That is simply a smooth function of frequency. Slightly deeper in, you get an oscillatory signature with a wavelength. You can compare it to, it's got a wavelength. The period is not very high. If you go deeper in, say at the base of the convection zone, you get a similar signature, but with a much smaller wavelength or a larger period. And we can see that both in solar models. This is a solar model. Now I've used modes from L of 5 to 25. This sort of, this sort of large wavelength signature is the helium ionization zone. If I remove this, get rid of the L dependence, you get the signature of the base of the convection zone. The amplitude of the signature at the base of the convection zone is related to how sudden the transition is there, so things like overshoot. The amplitude here, the average amplitude that I'll be using, depends on, if I were just considering a normal sun without bothering about, say, possible changes in temperature, it would depend on the amount of helium. But that assumes that the shape of the acoustic glitch is not changing. In the real sun, of course, the amount of helium is not changing, not over 10 or 12 years, But the signature of the ionization zone can shift or change because of changes in temperature that could be caused by magnetic fields. This is just another figure showing that we isolate this signature, we find the average amplitude of the signature, and then see, do we see any change at all? And in particular, do we see a solar cycle related change? So this is what we see. The average amplitude of the signature is on the axis on the left. Time is on the x-axis. The axis on the right is the 10.7 centimeter flux. If we just use modes from LF5 to 25, we see this change. If you squint hard enough, the first thing to note is that this change with time is not random. If you do any number of tests trying to look at the randomness of the signature, it is definitely not random. And you also see, if you compare it with the gray curve, that the amplitude is slightly lower at solar max than it is at solar min. The high degree data show something similar, but the errors and the uncertainties in the results are much higher. So instead of looking at just like this, we of course plotted it against the 10.7 centimeter flux. Sure enough, there is a statistically significant slope, a negative slope. So what you see in these figures are just different sets with GONG and MDI and HMI. The blue line is the slope with the 95% significant region marked in the dashed lines. The cyan line is simply a constant fit to the data. And we can see that the change is not constant. We did remove some of the really high activity points just to see if if our results, the slope is being affected by that. The slope is being affected by that naturally, but it's still a significant slope. Now, what does this mean? What is going on? Now, with global data, it's a bit difficult to see what's going on, but we do have some results from ring diagram analysis of the adiabatic index in active regions. So the upper panel, the black curve is a fiducial standard solar model. That's the second helium ionization zone. That's the first helium ionization zone and the hydrogen ionization zone. The colored points are the inversion results for 3 active regions. These are results I think we obtained in 2004. This is Basu, Bogart and Antia 2004. So what we see is that the shape is indeed different, and the depth of the second helium ionization zone changes. So we understand, particularly as you increase magnetic field. So definitely there's a link there to the magnetic fields. How do we convert it to a global magnetic field now? That is a good question. Douglas Goff had tried in response to a similar paper we had written with just half a solar cycle of data in 2004. And he claimed that our signatures are too big, but he had assumed that the shape is not distorted. It's mainly becomes shallower. So there clearly is more theoretical work need to be done to change this, to convert this into a magnetic field. Now let me get back to flows because I want to talk about the Tachocline a bit.
You have a couple minutes left, Sarbani.
Okay, so I'm going to go then straight to the Tachocline because you know enough about zonal flows. Except I like to show the zonal flows in this manner, where instead of latitude on the y-axis, you have depth on the y-axis and time on the x, because then you can see that the pattern, say at 15 degrees, the prograde pattern that we see at the surface, close to the surface near solar max, the pattern at 15 degrees starts at the previous minimum and then reaches the surface towards the maximum. So the question is, what does the shifting pattern mean? And I won't really, I don't know, but you can look at the pattern and say you already see the shift for the beginnings of cycle 25 here. So tachocline. We expect changes in the tachocline if this is where magnetic fields are generated. What you see here is a schematic of the tachocline. And what we looked at is this jump in the rotation rate between the rotation rate at different latitudes in the convection zone and the deep interior. We just call it the jump. This is sort of delta omega, if you wish. And these are the results as a function of time. Equator at the top, 60 degrees at the bottom. Again, gray lines are sunspot numbers in this case. And what you see is that the change over the two cycles is not the same at different latitudes. So my question then is this, are we seeing a magnetic cycle rather than a solar cycle? So will cycle 25 bring this branch upwards again? And the other thing is talking about fundamental changes in the sun. I can plot these changes as a function of an activity proxy, in this case, the 10.7 centimeter flux. And the two cycles are different even at the same level of activity. We can already see that in this figure, but this figure sort of hammers it in that the cycle 23, which are these brown and red points, the up and down arrow in the legend means it's the rising phase of the cycle, down means the falling phase of the cycle. And it's not a single relation. So again, is this a solar cycle thing? Is this a Hale cycle thing? Or is it just a fundamental nature of the change in the dynamo mechanism that we are not aware of? After all, we only have 2 cycles of data. Cycle 24 was very similar to the cycle in, I think, 1910. It's a pity we don't have helioseismic data from then. So I'm going to leave you with just a few thoughts. There are detectable changes in both dynamics and structure. Changes in structure are very small. I should say that I think now that I do see a small change in structure even at the tachocline, but I'm now trying to figure out how much of that result is systematic errors and can I account for all sources of systematic errors, so which is why I didn't show you that result. And the change in dynamics in the tachocline in cycle 24 was very, very different from cycle 23. And they do not have the same correlation with surface activity. I should remind you that if we look at frequency changes in cycle 24 and 23, the correlation with surface activity is not identical, but pretty close. So not this dramatically different. So of course, if there's any NASA folks or any NSF folks listening to us, we really need to continue monitoring the sun. 2 solar cycles is really not enough. We probably need 2 Hale cycles even to just start making sense of what we are saying. So thank you very much for your attention.